I'm going to dive straight in. Right, we've got a picture, and we're going to approximate the picture. And we're going to approximate the picture using H2O, of course. This is the H2O world. So what am I doing? This is a toy problem. I haven't been using H2O recently, and I wanted to go back and play with H2O and see the kind of things that I could do. So this is a toy problem. I've got source code on GitHub. What am I doing here? I'm taking my headshot. I'm treating my headshot as training data. We can think of an image as a function, right? You know, given an x coordinate and a y coordinate, we've got a red, green, and blue value. We've got a color for that pixel. So you could think of this as a big data set where every single pixel is a sample, right? Your x and y are your inputs, and your RGBs are your outputs. And then you could train a neural network with H2O, and you could approximate that function. And this is a bit of a cautionary tale really in a picture, because the model is not the data. All models are wrong. Some models are useful. This is also a cautionary tale, this picture. This is a warning about the dangers of extrapolating beyond your data set. So this is kind of a strange thing. Why would you do this thing? You would do this thing basically just to play with H2O, and because it lets you experiment with a model on a complicated data set, right? And an image is basically a complicated function. It's highly nonlinear, but there's structure in there, and you can model it very easily with H2O. And I thought it was interesting that you can take a couple of lines and you can make a little video like that. I like H2O. They didn't have to pay me to say that. But why ultimately am I here? Like, why is Intel here? Why does it make sense for Intel to be here? How do I even end up speaking here? I'm here ultimately because a long time ago, when I was a little boy, I read too many stories about robots. And the interesting thing about the robots was always the thinking of the robots, how the robots were thinking, and especially how their thinking went wrong. And because there were no job opportunities for robot psychologists, I decided to go and do some software engineering. And while I was doing the software engineering, I got an opportunity. My boss said, look, we've got this machine vision system. We're working on the machine vision engineer. He's gone away. You know something about computer graphics? You know, putting a picture together, taking a picture apart, it's probably more or less the same thing. You can go and work on that. So I went to work on that, and I started off with lots of programming. And after a while, I realized that with programming alone, I wasn't going to be able to get the product to work to the level of accuracy that we needed. The only way I could do that was with mathematical models. And not only did I have to use mathematical models, I found that the kind of maths that I'd done in secondary school, where it's step-by-step and it's deduction, you get an exact right result, you couldn't do that. The parameters of those models couldn't be deduced. They had to be inferred from the data. And once I'd done that, and once we got to the level of accuracy that we needed, I was totally hooked. It was really fascinating. It was a completely different way to do software. But at the time, I thought that it was kind of a niche, right? I'd been writing code for what seemed like a really long time, and just writing code had always been enough, right? Just handwritten code had always been able to solve every single problem that I tackled. But then I gradually realized that I was selecting the problems that I was tackling. I was only ever working on problems that you could tackle using machine learning, or using handwritten software. But most of the problems in the world you can't tackle that way. Like, what kind of problems can we reduce to software? Only those problems where we actually have an explicit understanding of how to solve them, right? You know, think of your high school maths class again, right? Your maths teacher doesn't want a result. You got to show them working step by step by step. Same thing when you're writing software. If you can't explain in excruciating detail how to solve the problem, right, it's not going to be software. Now, once upon a time, that wasn't an important limitation, because CPUs were tiny and memory was tiny. CPUs are not tiny anymore, right? We can basically manufacture as much compute as anybody wants. And we've got some fairly spectacular new memory technologies like Optane. We can give you as much memory as you could reasonably want. We can give you as much memory as you could unreasonably want. Memory and compute are not the bottlenecks anymore. The bottleneck now is the software engineer, right? And as long as the bottleneck is the software engineer, our CPUs are going to be locked in server closets, and they're going to be sitting there, right, adding up columns of numbers, and I don't know, storing and transmitting selfies and all of these entertaining things, right? And as much as I like taking selfies and transmitting selfies, right, most of the things that I want done don't involve selfies, cannot be done in server closets. I want something else to iron my shirt, right? I want something else to clean my floors. I want something else to do really most of my work so I can just travel around to conferences and talk to interesting people. We can't get there with software, we can only get there with machine learning. The Intel view is that if we can get rid of the bottleneck of the software engineer, instead of being kind of a niche operator with a $60 billion a year turnover, we can add 1 or 2 zeros to that number. But we can't really do that unless we have end users that are just doing machine learning all day long. Quick question, how many of you are actually training models right now, or at least this week? How many people in the audience? Okay, that's not too bad. And traditional machine learning, sort of statistical modeling, deep learning, how many deep learning folk? Okay, it's encouraging, the whole rest of the presentation really is about getting you as excited as possible so that you do as much machine learning as possible so that ultimately we sell as much compute as possible. And we want to get out of that server closet, we want to get all the way out to the edge. This is an example of the edge computing. This is a Movidius compute stick. 2 trillion operations per second for less than 1 watt, right? It's not a lot of power. It's nice. This is actually the main technical tip, nothing to do with H2O. If any of you, ladies and gentlemen, are writing in Python, do try the Intel distribution. It has been heavily optimized by people with intimate understanding of our silicon. It is a really easy way to get better performance. Okay, onto the use cases. Somebody's looking at a clock. Right. There's an unfortunate association between AI and, I know, movies like Terminator, right? And for that reason, Intel wants to make sure that people understand that AI can also be used for good. That is an option. And for that reason, we've done some projects that are not necessarily obvious Intel projects to do. There's an organization called the National Center for Missing and Exploited Children. It's a non-profit in Alexandria in DC, basically. And they operate as a kind of a clearinghouse. If you are a very large tech company, like a very large social media company or a very large internet search company, from time to time your users will do things that distress you. They will upload images that appear to be child sexual abuse material. What do? Well, you send what's called a CyberTip to the National Center for Missing and Exploited Children. And they will look at the data in your report and they will decide which police force, wherever in the world, should be notified so that they can go and take action on that report. Now, the thing is that these tech companies are being extremely cooperative. They're really doing a lot to discover this material and to forward these reports. And because they're very big tech companies, they've automated this. And this means that the nice people at NCMEC are experiencing an exponentially growing volume of reports. However, they're a non-profit and their financial officer has reservations about the exponential hiring of analysts. And so for that reason, they were wondering if we could help out with a little bit of machine learning. Well, was there data available? There was really quite a lot of data available because they get a huge number of reports and their analysts process a huge number of reports and conveniently they store all this stuff in a relational database. They did tell us that the reports were free text and we got ready to do some really serious natural language processing. But first we kind of sat down and we read through a lot of reports, just literally read through a lot of reports ourselves. And kind of very quickly there was a certain sameness about the reports. And then we realized that the nice people at tech companies found that there were limitations in the schema, the report schema that NCMEC gave them, and they worked around the limitations of the schema by jamming everything they could into the free text field. So they'd take their own schema and they would run it through a template and generate what looked like a report type of human but wasn't. Right. It's unfortunate, right? There are better ways to do this, but that's the situation. But once we realized this, it meant we didn't need to do the fancy NLP, it meant we could reverse engineer the template, saved us a lot of trouble. It is really worth just trudging through the data yourself, in my experience. You will find things that you didn't know you were looking for. Did we have ground truth? Ground truth is a tricky one. We knew where the analysts sent the reports. We didn't know whether the actual police officers receiving the reports felt that the reports that they got should have actually been sent to their jurisdiction in the first place. Didn't really have ground truth in that sense. So we had to accept we would have to treat the analyst's opinion as ground truth. But I am a nasty, cynical person, and I didn't trust the analysts. But these nice ladies were very patient with me, and I gave different expert ladies the same sets of reports and had them decide separately, independently, where the reports should go. And I found that these expert analysts agreed with each other about 92% of the time. And this was a really important number for me. If I had just taken where the report's been sent historically as my label, as my target, maybe our customer would have wanted me to get a model that would agree with their results 99.9% of the time, right? which is not achievable, right? Because they couldn't agree with each other more than 92% of the time. So that gave me a really good target. It also was reassuring because it meant there was actually a signal there in the first place. It could have been that they were just outputting noise, but they weren't. Actually, user trust. A lot of people talk about user trust and explainability. Explainability is a wonderful thing. In this case, we did try using highly explainable models and less explainable models. And we found that, at least in this case, our customers really, really strongly preferred to have a model that was really, really accurate over one that they understood. They felt that it was sufficient to have a really good result, and if they had a question, they could go back and look at the inputs themselves, being that they were experts, and they would decide whether or not they agreed. And we found that after they'd seen a few hundred reports and looked at our outputs, we built trust simply by experience, by demonstrating that the thing actually worked. Lessons again, XGBoost. Everybody says this, but it's true. If you have structured data, XGBoost is a really good first thing to try. And again, don't be afraid to test the humans. People are really nice. I felt bad at first. Would you mind going through 500 reports and just tell me where you think they should go? No, people don't mind. If you can automate a really boring part of their workload and free them up to do something that's higher value and more complex and a better use of their time, they're delighted to do 500 very boring things. Right, different use case, but same general problem space in a way. Thorn is a non-profit. It's founded by Ashton Kutcher and Demi Moore. They're both Hollywood people, but Ashton Kutcher is also a tech investor, a bit of a West Coast tech mentality. Ashton felt that not all police forces are good at building sophisticated software tools or even commissioning them. And both of them felt that there was a bit of a gap there that could be filled by non-profit that would build these tools and make them available to law enforcement officers around the world for free. So it turns out that they have a lot of problems that look suspiciously like machine learning problems. They've got a tool called Spotlight, right? And Spotlight is there to help fight sex trafficking. If you're a law enforcement officer, one way to do that is to trawl through all the sites where people advertise girls, and another way to do it is to use the Spotlight tool, which apparently increases their productivity dramatically because Thorn do all the kind of hard work of scraping and munging and cleaning up the data and that kind of stuff. So the good thing here is that the guys creating the problem are in a way helping to solve it. These pimps and these sex traffickers acquire underage girls, 14 or 15. They're much easier to control. It's great business. But then they have a problem, right? On one hand, they really need to market as much as possible, and the internet is a great marketing tool. On the other hand, it's also a great way for law enforcement officers to find them. So they feel a certain delicacy about advertising the age of these girls. But at the same time, some customers prefer really young girls, and so there's pressure on the pimps to advertise the youth of the girls, but to kind of use euphemisms and not flat out say, I've got a 14-year-old available for rent. So from a Thorn perspective, right, this means that the data they need to solve the problem is being made available by the offenders, right? So that's good. That's ultimately a good thing. So how do we want to help them? We want to help them by having to prioritize the ads people should really be looking at, right? Since these ads have text and photographs, we felt we really ought to be able to use those photographs to find the underage ladies and direct the attention of all those 8,000 police officers to these young ladies so they can go and ask some difficult and searching questions. We actually thought there might be an off-the-shelf model that they could go and use, but it turns out that the models out there for age estimation tend to be built off some academic data sets where the labels are not so very precise, and also the demographics don't match. A lot of the academic data sets are focused on famous actors. A lot of those famous actors are kind of European looking and men and in their 30s, 40s, 50s. Just not a good match for the demographic we care about, which is, in this case, right, your teens through your early 20s, fairly strong kind of Hispanic component, East Asian component, right? So we kind of bit the bullet and we built our own data set. It's not easy, it's painful, but it's worth doing. It's worth doing. Now, I'm not really an expert, right? I don't have a doctorate in this stuff. There are commercial products there. We built a benchmark first. We couldn't even measure how good they were. Had to collect our own data to measure the performance. Also had to measure human performance because, right, how old is the lady anyway, right? How well can you do that from the face, right? Ladies do things with hair and makeup. These are technical things. I do not understand these technical things, but I know that they happen. Maybe they're confusing, right? But empirically, I hired some people. I paid them to estimate the ages. I compared their estimates to the ground truth, and I find that if you get 3 people that are reasonably good, and if you average their judgments, you can get reasonably close, right? You can get to the point where you've got some hope of ranking these ladies. So the 14-year-olds and 15-year-olds are at the top of the list, and maybe the older ladies that are less likely to be controlled in the same way are further down the list. So the thing is possible in principle, and then we can crack on with the machine learning. Again, it's just a data problem. You just need to get lots and lots of data. It's easier than I thought. It turns out there's an app called Instagram, and people post lots of pictures. The pictures are dated, and if you're a famous person on Instagram, also your date of birth is known, so you can get data where the age label is accurate within a week. It's remarkable but true. I had no idea. Accuracy is not yet as good as human, but we're going to human parity. We're just going to go there. We're going to keep getting data, we're going to keep cleaning it, and we're going to get there. We're far inside the commercial results, we're inside the academic results, and really the lesson here I'm trying to tell you is that you don't really have to have a doctorate. Even if you just really care about the problem and you don't mind getting the data and labeling the data and just kind of trudging through it, you can get state-of-the-art results and you can make progress on problems which are really, really, really important. You should feel these things are very possible and very doable, and you should be ambitious for what you can do. It's not that hard. You just need to stick at it. Yeah, text. We're going to use the text. We haven't done it yet. Text is important. Turns out young people use things called emojis in great variety and great number. We've got summary statistics on that. Eventually we'll have a model on that, and we'll combine the text and the images, and we will grind on that problem. How am I on time? Really good? Okay. Right. Totally different. We've left the sex trafficking world behind and the horrible things. I want to mention a very nice thing that is maybe underappreciated. The previous speaker talked a lot about embeddings. You should be listening and you should be using embeddings. If you're not using embeddings, learn about them and study them. They're not really that complicated a concept once you roll up your sleeves. They're right there in H2O. I used to work in text classification a lot. And when I started using word vectors, it just was the easiest way to make things work better. It really was. It was remarkable. Because at the end of the day, right, you don't care about matching words lexically, matching words by spelling. You care about matching words semantically by meaning. Right? So why are we using tokens again? Right? Embeddings, it just makes sense to use them. Doesn't necessarily help your precision, but again, recall gets a lot better. It's easier to understand why that is. All of a sudden, you're a lot less sensitive to the exact spelling that people use or the exact words that people use. There's another benefit, though. I think a lot of people weren't doing this, but we were. We cared about more than one language. We cared about 30-plus languages. Again, we're not familiar with 30-plus languages, and because of a natural laziness and disinclination to work, we don't care to do special engineering for 30-plus languages or data labeling for 30-plus languages, even though I said in the last use case that you should label lots of data. Anyway, we found that even among very different languages, you get common patterns with word vectors. Basically, words that are highly related in one language, similar sorts of words can be highly related in another language. So in English, words to do with food occur a lot in similar contexts. That's also true in French. It's also true in German or Spanish or Italian. It's probably true in lots of other languages that I haven't thought about. And it turns out that if you have word vectors in two different languages and you've got a dictionary of words between those two languages, a small dictionary, even a few thousand words, you can calculate a transformation that will map the word vectors from language A into language B. And now, boom, all your English labeled data, people usually have a lot more English labeled data than anything else, now counts as labeled data in the language of your choice. Just for fun, we tried a classifier that was already pretty good at classifying English documents. We tried on Romanian documents, having first mapped the Romanian word vectors into the English coordinate space. Right, no other work done, zero training. Boom, we got not spectacular accuracy, but decent, respectable accuracy for zero labeled data. If we'd actually bothered to label any data, we probably could have gotten quite good results. So that tells you how far we'd gotten away from the world of spellings, right? Because Romanian and English, the spellings are not that similar. Yes, there's a Latin influence in both languages, right? But they're, I can't read Romanian. I can read English a little. I had a really painful few months once working on a network traffic and anomaly detection problem. This is a security thing. We hope that by analysing logs from web proxies, we'd be able to find strange bad things happening. Because the thing about the new bad things that people do is that you don't know what they look like, so you don't know what you're supposed to look for. It's a nasty kind of problem, especially because these things are rare, so you mightn't find them in the first place. And if you do find them, you don't know what they look like, so maybe you won't know you found it and you move on. We tried a lot of what I would call traditional anomaly techniques. We read a lot of papers. A lot of people had their pet techniques. We found a really great resource on GitHub, a really interesting benchmark, lots of time series with actual real-world anomalies. That was really valuable. So after months and months of trying, things were difficult and complicated and took us a lot of time. Somebody pointed out an anomaly detection feature in H2O. Okay, we'll give it a go. Anybody familiar with autoencoders already? Right, one gentleman's nodding his head, the rest of you are silent. An autoencoder basically just tries to take what goes into the model and then give you back the same thing, right? You would think that would be easy, right? Whatever the user gives me, I'll multiply it by 1 and that's the answer. So with an autoencoder, you impose some restrictions so that to give you back the same answer, it's got to first find a simpler way to represent it. And the intuition for anomaly detection would be something like this. Even though none of you could repeat my talk, I don't think, or hopefully couldn't, you could probably give somebody a sense of the more important bits or more relevant bits, or the bits that made sense if there were any such pieces. So you're taking what I said, you're finding a simpler representation, and then you're reconstructing it for your new audience. How do you turn that into anomaly detection? If you take the signal that you trained on, you should be able to go to reproducing it because you trained on it a lot. If somebody gives you a new signal that's from a different distribution, your reconstruction error will suddenly go up. Níl tá mé caint scéalga níos, agus ní éalga guibh, agus, yeah, now you don't have any idea what I'm talking about because I'm talking in Irish, but you can tell something changed, you can tell there's an anomaly. You didn't know you were waiting to listen to Gaelic or Irish, but when I switched, you probably noticed. That's simply the intuition with autoencoders. The autoencoder gets bad at reconstructing the signal, something's changed in the signal and don't know what. But the key thing is that the thing you're looking for doesn't have to have been in the original training set. Anyway, we tried it out. It probably only took a few hours, and then boom, it blew all the rest of our results away. It was really cool. Highly recommended if you need to do anything like that. Somebody in Intel said that all of you have to read this carefully. I don't know why, but apparently it's very important. You have been a lovely audience. Thank you very much.
We have a question basically to have whether do we have Intel optimized platforms delivered through Anaconda?
Oh yes, we do. So for example, if any of you, nice ladies and gentlemen, are using TensorFlow, installing via Anaconda is a really good way to install it. I recently tried out with a genomics use case. I was running a CNN over some genetic data. I got a 10x speed up when I used the Intel optimized version of TensorFlow. I found that personally significant. That was one really good example. Yeah.
Any more questions?
Thank you very much. 2 questions actually. Do you have an optimized R version for Intel architecture?
That is a really good question. I'm not sure. Are they using the MKL yet?
Yeah, the MK libraries. So optimize MK libraries you can actually leverage through your R program as well. Yeah, I mean.
MKL is the math kernel library, and it uses lots of Intel instructions.
Yeah. However, as we are mentioning that, whether it is within the data center or whether it is at the edge, leveraging those Intel library functions, whether it is MKL or Intel optimized TensorFlows, we believe that that is going to provide you the performances depending on leveraging those library functions in your application can provide much more better performance kick once you actually use Intel Python. Intel version of Python and TensorFlow, which is optimized by Intel, which basically leverages all the underlying library functions. You had another question?
Yeah.
Thanks. So, what did you do after the word embedding in your model? So, you did the word embeddings to transform the data, the text into vectors.
Yeah.
And what did you do after that?
So when I was classifying those documents, once I had the word embeddings, it was fairly easy to, you can simply add some word embeddings sometimes, add them together to summarize a short snippet of text. Yeah, they're fairly easy to work with.
I mean, did you use the word embeddings version then of the text as input to another?
Sorry, yeah, so yeah, exactly. So the word, yeah, once you use the word embeddings, that was then that was the engineering we were doing to the features to go before we went into the model. So the model never saw the raw text. The model was trained on the word embeddings, and that turned out to be a really good decision. A little bit more computationally intensive, but that's a good thing if you work at Intel. Yeah, and the recall was a lot better. Right? We couldn't reasonably have got there by labeling more data, or it would have been very, very expensive. It was much cheaper to use the compute cycles rather than the human labelers.
Yeah, I did something very similar, but the data I have had no labels, so I used clustering algorithms. So,
Yeah.
And it helped me actually to cluster the different.
I imagine that worked beautifully, the clustering on the word vectors.
Yeah, it was way better than you could do with text.
Yeah, you want to cluster by meaning, not usually by spelling. Yeah. Yeah.
The word embedding version that the output of the
Yeah.
word embedding was used as an input to a clustering algorithm.
Yeah.
Which in my case it worked very well, I think.
Yeah, if you're doing natural language processing, you haven't looked at word vectors yet, it's time to start. Okay.
Thank you, Ed and Swastik. Thank you so much.
No, thank you.